Welcome everyone to the July 28th Open Planetary Lunch, and I will be presenting my own research today. These are slides from Scott Fleming, who's my collaborator on a lot of this, and this is a talk he's been giving, and I hoped he could give it, but he's on vacation. So I'm going to give it, I will probably diverge from the slides pretty quickly because I want to talk more about the technical aspects, and this presentation is more for the astronomers who are interested in doing science with these tools, whereas with this crowd, particularly the 7 or 8 people we have, I'm interested in talking about the philosophy and the technical approach to what I've done here. So this is a project called gPhoton, which I started around, I had the first idea around 2008. It is a project to refactor how the GALEX space mission represents all of its data in the archive so that we could enable new kinds of analysis with those data. So I think there's a slide that describes the GALEX mission. The GALEX mission was an all-sky ultraviolet survey in 2 bands. It was a small Explorer mission, so a very cheap mission, but it returned a tremendous amount of data. It's 130 terabytes in the database, so that's the calibrated data. Unlike with some derived remote sensing data sets, the data volume does not expand dramatically when you start producing derived data. So it produced this tremendous amount of data over 10 years, observing the sky in half-hour chunks. 26 minutes was the longest it could observe at once because it had to be in the shadow of the Earth in order to observe the ultraviolet so that it wasn't contaminated by stray light from our sun. The detectors were microchannel plate detectors, which record the position and time information of every photon event. So as a photon arrives, we call them photon events. As a photon hits the detector, it hits the charge multiplier plate, which creates a cascade of electrons, and then a grid of wires reads out, the differential time of arrival, gives you the X and Y position as well as the actual time of the photon arriving. Now the mission itself only released, there's a picture of the detector, and Scott explaining how charge multiplier works. And that is the eclipse information. So the mission itself only produced 2D images on the sky like this one. The spacecraft actually dithered over the course of a whole mission to avoid depleting local areas of the charge multiplier of electrons. And then we used the aspect solution from the spacecraft to reconstruct images that had nice point sources like this one. The mission team, of which I was a member, only released, for practical purposes, only released images like this, which had total integration times between 2 minutes and 26 minutes, depending on the observing mode. So, but at the same time we had, and there was also a GRISM mode, that's what the GRISM of the slitless spectroscopy mode. At the same time, we had photon data for the entire mission. So we had these time of arrival and position events at 5,000th of a second time resolution. And it occurred to me late in the mission that we could recalibrate the entire mission so that we could get to the actual photon events and create light curves of the sky at arbitrary time resolution. And you may, many of you being planetary scientists or sociologists may wonder why we would care about things at those time resolutions, and I'm unable to show you. But there are things in this would be an amazing picture of a flare that occurs over a couple of minutes. So a star goes from something like 18th magnitude to 14th magnitude in a span of 2 minutes, and then drops back down to its original magnitude. There are a variety of types of variability, of stellar variability on those timescales. Flares are the best ones in the ultraviolet because the flare itself is a black body that peaks in the ultraviolet, so the flare itself is the brightest in the ultraviolet, whereas the M dwarfs on which the flares occur are relatively dim in the ultraviolet. So we have tremendous contrast in this wavelength, which is also hard to observe from the ground. So the data is particularly good for that, and that is a lot of what we have studied. But there are other things at these timescales that are enabled by the photon level data. So he doesn't get into the technical bits, which I wanted to talk about. So we had 10 years of data. These are each raw data file is several gigabytes. We recalibrated all of the data so that we had a database where every line of the database was a single photon event. And the result was, I think the final number was 3 trillion entries in the database and about 50 columns and 130 terabytes. And when we first conceived of the database in 2008, and then when we first started building it in 2011, it would have been one of the largest public-facing databases in the world that can actually be queried in real time for scientific analysis. It's not anymore, but at the time that the Mikulski Archive at Space Telescope that hosts the database, at the time we created this database there, it was definitely their largest database. Of course, since then they have TESS and LSST is coming, and Kepler is an increasingly large database. So one of the things I wanted with the software is that it would be very, very simple to use, even though there was a tremendous amount of, many, many years of software development that went into recreating the calibration pipeline in Python. The original pipeline can no longer be used. It's decayed from bit rot. There was all this pre-work to getting to the point where you could use the data. I wanted the data to be actually incredibly easy to use. So what you see on here is a command. It is a one-line command in Python plus the import that creates what you would have seen, which is a movie, a movie of half hour of observation with 30-second time resolution that is calibrated, that you can do science from right away. And you can also then choose a point on the sky. In this case, that is the location of JG 3685A in decimal degrees, and a time resolution, which is the step size. And in one line, you can create a light curve of the data. You can create that at 1 second resolution or 10-minute resolution, depending on what your science case is. You can rapidly change how you're analyzing the data. So here's how the database was broken out. Bernie Shao did a lot of work to make the database fast. So to create a light curve like the one I saw on I showed you on the previous page might take 30 seconds, and then that's with the overhead of querying the database and the HTTPS and all of that. We can go into details of that if anyone is interested. So there were some principles that we had in mind when we first started creating this tool, which is, first of all, that we wanted no naked SQL. We wanted to be simple syntax in terms that astronomers understood, like the size of the light curve bin and the degrees. We also wanted to be really easily installable, which now is a little more standard as far as Python tools, but we started thinking about building this in 2008. AstroPy was not mature by the time we started programming this. By the time we got a few years into it, AstroPy had matured, and we actually had to refactor code to include AstroPy, to include functions that we'd written around. We also wanted to be use case agnostic. I think this is a really important thing for an archive, and Anne has talked about this too, which is that I didn't want to design a tool that only did, for example, flare science. I wanted it to enable a wide range of science, things that I could not even imagine doing. One of the ways we've done that is, so we have the tools that create the images, and we also have the tools that create the light curves, but we also, when you create a light curve, in the data structure that is returned to you is a table of every photon event within the aperture that you fed to the tool. So you can do it, those are calibrated photon events. You can do anything you want with those. You can create your own images. You can slice them how you want if you want to carve out weird shaped pieces of sky or something. It also needs to be fast. So we spent a lot of time optimizing code, especially the database queries. That was really difficult. There were some database queries where I could construct a query that would give me exactly the answer, but it was faster to construct a different query that was more performant for various reasons, and then handle some of the processing in the Python rather on the SQL side. And then we also wanted to be very easy, a very, very, very short learning curve. I've encountered a lot of people who sort of don't want their data to be used easily because it will be used wrong. We tried to mitigate against some of that. We have flags for situations where we know create common problems, but it was also my opinion while creating the tool that the people using the tool were responsible for their own science. So I would give them as much information as they needed to make an educated decision about whether some artifact in the data was astrophysical or instrumental, but I wasn't going to create a barrier to entry for using the data. So we created a couple standard tools. gPhine just gives you, is there coverage at that point of sky? What is the coverage at that point of sky? This turns out to be the only way to determine this information. That wasn't information that was provided by the mission. Just the way the catalogs were constructed, it didn't include that information. You can also use GMAP to create images or time series, which astronomers will call cubes. Most people would think of them as movies. For any position on the sky, you can adjust the pixel size if you want. And then gAperture creates light curves as a function of time given an aperture. So I'll rush through the science, I assume, and also the movies don't work. I'll rush through the science because I'm assuming most people here don't matter that much, or don't care that much about it. But we have cataclysmic variables, white dwarf pulsators. So this, Michael Tucker was an undergraduate student who had a first author paper. I think he's a PhD student at Hawaii now. We've had a lot of, partly I think because the barrier to entry is so low, we've had a lot of first authored papers by undergraduates come out of gPhoton, which I'm actually really proud of. We have these eclipsing binaries. So this is one star eclipsing in front of another star and causing its flux to literally bottom out. The time bends here, I think, are 30 seconds. So you can see the star, which has some sort of standard brightness, just bottoms out for, say, 5 minutes, and then it comes back. It's similar to Kepler observing a planet or transiting a star. So this is a star transiting another star. This was never expected to be seen by Galax, and in fact, before this tool was created, you could not have detected this in Galax. Here are some more examples of those. In this paper, where Michael Tucker was the second author, and I think his student, so we're now in the second generation of students using gPhoton, was able to put a limit on transitors based upon just this little bit of data from Galax. Which result I don't really understand, but it's cool. And then we had another student, Thomas Boudreau, who did work on pulsating subdwarfs. And there's frequency analysis here. You see the lower curve is the gPhoton light curve, and to an untrained eye that can look like noise, but when you do the frequency analysis, which is what appears above it, it actually has a dominant peak frequency that is not an instrumental artifact. We do have instrumental artifacts that look like variability. The one on the left is what we call a hotspot transit, so that could look like a star transit, but it's actually where the hotspot mask goes over the aperture. And then the things on the right are situations where the flux is heavily correlated to the detector position and the exposure time. There are a bunch of reasons why that sort of false positive occurs, which I can go into if someone's interested. And then the stellar flares. This was Clara Bressuer's work, where she compared Kepler coverage with Galax coverage and looked for flares in both of them, and was able to find flares in the Kepler data that looked like the tiniest, most meaningless bump. So the Kepler data is 30-minute cadence, and the Galax data can be 1-second cadence if you want. Which means that the flare, if it is a small flare like this one, is well within the bin of one Kepler. One Kepler bin, which is, I believe, what those vertical lines are in the middle. And yeah, found a whole lot of flares that would not have been found in Kepler otherwise without Galax. And then more recent work by Scott, which we have in review, is that we found short period quasi-periodic pulsations on stars, which I also don't expect planetary scientists to understand because astronomers don't understand them. But there are only a few examples of these, so this was very exciting. Quasi-periodic pulsations are these ringing in the signal of stars. We see them on the sun. We only have a few examples of them on other stars, and when we do have examples of them on other stars, they tend to have periods or quasi-periods of, say, half an hour. And we have found a couple examples now where we think we found quasi-periodic pulsations with periods of minutes or seconds, which are typical on the sun, but not on other stars as far as we knew. So we hope to find more of these. I also know there's one, so that we know it's not an instrumental effect. Park Lloyd has HST data in the ultraviolet where he's found a similar signal there. So we don't think it's just a Galax artifact. And then finally, my most recent work is to again recalibrate all of the Galax data, and this time mine every single possible source in it for variability. This is not possible with gPhoton because gPhoton was really designed to do one star at a time. So in order to do all of the stars, I have to recreate the full frame movie images, which is not as, which is slower, especially over the web, hitting the database. It is much, much slower. So I've had to rewrite parts of the pipeline to regenerate new images, double check the calibration, make sure that's correct, and then create a source extraction pipeline that finds all the sources, extracts the light curves. So what you see right now, I presented at AAS in January. These are 400 of the 402, what I call 6 sigma variables serendipitously observed by Galax over its 10-year mission. I eliminated 2 because they messed up my pretty grid. But there are all sorts of variables in here. The flares are the sort of spiky shapes. There are a couple eclipsing binaries, which you can see. I think there are 2 asteroid transits in this data, so where an asteroid actually passes in front of another star. And then there are a bunch, I would say 10% of these light curves, we still have no idea what they are. We haven't started doing the cross-matching to the known variables. So that will eliminate some of those, but I expect 2 or 3 of these light curves to be completely new objects, not necessarily new types of variability, but maybe. And that's just the 6 sigma pass. I'm working on the 3 sigma pass now, and I expect a lot more, maybe 10 times more variables to fall out of that one. And then just different ways of me representing the data. These are all cases of false variability, which you probably don't care that much about. The one right in the middle is a satellite. So that is a human-made satellite in Earth orbit that looks like a flare in the light curve. If you don't then look at the image and see that it's streaking across the sky. So probably recent projects by Elon Musk and others will make that situation a little bit worse. And then these are cases of true variability. I don't know what the first one and the third one are. The second one is probably a flare, and the last one is probably one of those eclipsing binaries. And then just to prove that even things that look like noise are real variability, this is a star that triggered in my search criteria, and in 2 visits, it has the same sort of noisy looking variability. So to explain the plot on the top, the red line is the 2-minute light curve from images. The black line is the 30-second light curve from gPhoton, and the blue envelope is the 3 sigma error bars from counting, and counting is all that really matters for galaxy data. So in 2 separate visits, this same source, which is the only source in the field that triggered as variable, and with the same sort of ambiguous variability that we don't know what it is, but I don't think it's fake. So it's very exciting that things like this, which you wouldn't be able to pick out by eye, are being picked out reliably by the algorithms.